Welcome to solverfy.
We're asked to find a connected weighted simple graph with the fewest edges possible that has more than one minimum spanning tree. So we have that if the graph is simple and connected and has more than one minimum spanning tree, then of course the graph cannot I should say the weighted graph. Simple and connected, it has more than one minimum spanning tree, then the graph cannot be a tree itself. Otherwise, we would only have one minimum spanning tree, which is the graph itself. And since a graph on n vertices, or I guess I should say a tree on n vertices has exactly n minus 1 edges, it follows that the weighted graph should have at least as many edges as vertices. So for this problem, there are many different, infinitely different graphs we could pick that would be a solution. For the simplest examples, suppose that the graph has 3 vertices. Let's try and find a graph that has 3 edges. If we can do this, then it follows that this graph has the minimum number of edges and still has more than one spanning tree. Because if we only had 2 edges, then we would have a tree already. So consider if we have a graph with vertices A, B, and C, and because we have 3 edges, we obtain a cycle, and let's label the weighted graph so that each edge has the same weight. So 1, 1, and 1. Well, then it follows that for this graph, the graph with edges AB and BC is a minimum spanning tree, as well as the graph with edges AB and AC, as well as the graph AC and BC. So these 3 graphs are all minimum spanning trees. Now, if we were to neglect the labels on the vertices, then it follows that these graphs would be isomorphic. So this is kind of a special case. But already here we have an example of a graph on 3 vertices, which has the minimum number of edges such that the weighted graph has more than one minimum spanning tree. For another example, let's consider if we had 4 vertices. So now suppose our graph has vertices A, B, C, and D. We want our weighted graph to have at least 4 vertices and 4 edges. Let's draw an edge between A and B, between A and D, between A and C, and between B and D. And let's label the edges, all with a weight of 1 again. So you see that this graph has the minimum number of edges for a weighted graph such that it's not a tree, and we notice that the subgraph with edges AC, AD, and AB is a minimal spanning tree. Just draw these in green so we can distinguish. We also have that the subgraph AB with the edges AC, AD, and BD is a minimal spanning tree. And of course, we also have that the graph, or the subgraph, with edges AC, AB, and BD is a minimal spanning tree. So it follows that this weighted graph with the minimum number of edges has 3 minimum spanning trees. So here's another example on 4 vertices.